Would be there. So no sense. Yeah. So there's the leader. This is still. I guess it's yeah. There's like
Hey, we're going to work through packet 2. If you guys can have packet 2 out.
It's not really
Okay, let me just go through the updated calendar for a minute. I know that I keep the assignments are not entirely correct in your packet, but just kind of run through what we want to do here. The packet that we're going through has a lot of first semester topics in it, so I want to kind of run through some derivative topics. So tonight, you guys will work on pages 5 through 8, and then because you guys don't have the updated calendar assignments, I'll send out a remind every day of what's due the next day, so there's no confusion in terms of wait, what's the assignment. So tomorrow, I want us to work on particle motion and first semester theorems. And you guys will we'll work on pages 9 through 12. We'll kind of skip around, and then whatever we can finish, you guys will do for homework. And then we'll kind of focus on maybe a little bit of the calculator active problems, what calculator questions look like on the AP exam, and that will be due on page 10 to 16 will be due on Thursday. But I am going to start the next FRQ packet. So we are going to have a FRQ quiz the Thursday after we get back. So I want to kind of highlight some of those packets. So we're going to work through that Thursday and Friday as we're finishing up packet 2. And then after break, we're going to, we should be able to get through a good chunk of the packet 3. We'll review a little bit of that, but also want to start multiple choice review because the 2 weeks that we come back from break, we're going to have quite a bit of assessments. We're going to have a FRQ quiz, or sorry, FRQ, it says test here, but it's just going to be a quiz. FRQ quiz over differential equations and Riemann sums. And then the following week, I'm going to split up the multiple choice test into 2 days, part 1 and part 2. Part 1 will be first semester topics, and then we'll review second semester topics, and then you guys will take second semester topics of multiple choice. And this will be a test grade. So I'm still working on finishing grading your FRQ test. Hopefully that'll be in by the end of this week. And then we have a quiz coming up Thursday after spring break, and then test split into 2 days the following week. And after that, you guys are just working on trying to finish packets 5 and 6. And as far as packet 5 goes, we're going to spend most of that first week of May doing the prop. We'll probably get through like 3 in class, and then you guys will probably try to do 2 or 3 for homework. But so we should be get through packet 5 without any issue. It's just that packet 6, we're not going to spend much time in that until the week of AP exams, and by then that's the last week for seniors, and you have AP exams going on. So that's why I want to give you packet 6 early so that you guys can start working on that. The way I'm going to grade packet 6 is just completion. Right. So if you show all your work and you're checking your answers with the solution key on the website, and you'll get 100 points. But if you're only completing a portion of it, then I'll just give you a percentage grade based off how much you've completed. But ideally, everyone gets 100 on packets 5 and 6. Yeah. All right. So turn to page 5. Some of these derivative topics, I think, are ones that we should be pretty comfortable with. So I just kind of want to run through the steps that we will expect to take. But I think for some of the easier problems, I want us to just try these on our own later. And I want to maybe talk about problems that or concepts that we may not have seen in a while. And I want to spend the time in class to go over those and leave the ones that I think you know how to do for you to do on your own. So page 5. Number 1, notice that all these terms are nicely separated. Most of these are power rule. So I'm just going to write down what we expect to do. So there's power rule for derivatives. There's derivative for e to the u, and then there's natural log of u. So a little bit of, but we know how with power rule, if we just bring all the variables up, get it ready to be applied. Remember our power rule conditions. 3 things here. Make sure that your variables are converted. Radicals are converted to rational exponents, and that we can't do power rule if the variable's in the denominator. It has to come up to the numerator. And then finally, if you see any parentheses, that you expand and distribute before you do power rule. Number 2, anyone know what rule is best suited for number 2? Got a function within a function. So what do we use for that? Chain rule, right? Okay. So just to set it up. Again, I want you to do these on your own here. So this is chain rule. And you do want to rewrite it. And then you're taking turns with each portion, right? So the outside portion is the bracket to the 1/3. And the inside portion is the 5 minus 3x squared. And you're taking turns with each part. Okay, number 3, find the equation of the tangent line. So you have a numerator and denominator. Make sure you don't just say power rule, power rule. We got to go through quotient rule. So f prime g minus f g prime, r over g squared. And then you get your slope. You plug in 1 to get your order pair, and then point slope form. Number 4, find the derivative. What's involved here? What do you see? X squared times sine 2x. So product rule. Yep. So you got to go with the product rule. A little bit of chain rule. Sine of u becomes cosine u times u prime. So I'm hoping that you guys can just try these on your own. I want to just kind of talk through our strategy to start these problems, but then hopefully you guys find these pretty straightforward because we've been seeing these recently as well. Okay, next page. What I feel like we haven't seen in a while maybe is implicit differentiation. So implicit differentiation, we apply this method when an equation doesn't have a y equals. When your y is kind of stuck inside the equation, there's multiple y's or there's something done to the y. So we're still going to find the derivative like we normally would. It's just that when we come to our y variable, we're going to take that derivative and then attach a dy over dx. So we just have to do a little bit extra when variable y is involved. And then after we find our derivative, depending on how many y variables there are, that's going to basically produce, every y variable will produce their own dy dx. So however many y's there are in the equation is how many dy dx will pop up. And then we're just going to algebraically move things around, try to get that dy dx by itself. We don't have to do that with functions. Functions is just y becomes dy dx, and it's already by itself. But when we have equations that are not functions and the y's are kind of mixed into the equation, we typically have to do a little bit of algebraic work to kind of get that dy dx to be by itself. Okay, so let's go through a couple of examples of that. X squared plus y squared equals 5 plus y. We know there's implicit involved whenever it's not a function, right? And typically that's easy to tell when your y's are either out of place or you see multiple y's in the equation. Okay, but we're just going to apply derivative like we normally would. X squared becomes 2x. Y squared 2y, right? We find the y variable like we normally would. Nothing's different. It's just that we need to add a little bit extra, and that extra is having to include that times dy dx. All right, 5 goes to a what? 0. And then what's the derivative of y? And let me ask you, what's the derivative of x? 1, right? So y's derivative is also 1. Yeah. And then we're done with the derivative, but then we're involving y's derivative, so we need to include times dy dx. I really like students putting a 1 there. It's not wrong if you leave out a 1. It's just that when you later on, when you have to factor dy dx out, seeing that 1 there is a good reminder that, oh, there's something left over. That so if you don't have that 1 there, typically I see students tend to forget, oh, I need to put a 1 in place of that term, even though that dy dx got factored out. Okay, so now we're done with the calculus. Now we're just trying to move things around to eventually get that dy dx by itself. So I'm going to group my dy dx terms on the left side. Okay, factor the dy dx out. And then we're left with 2y minus 1. So I think that's why that 1 there is so helpful. If that 1 wasn't there, I see students factor the dy dx and they just put a 2y and forget that, oh, there's still something there. So having that 1, I think it's a good placeholder for us. Okay, so now dy dx, our slope, basically dy dx is just a derivative equation. You give it information in the formula, in return, it'll tell you how steep the graph is on this curve. Number 6 is a bit more involved because obviously there's y's involved. We got to go through implicit, but 2xy, what's involved here when we have to find the derivative? Can I just say 2x becomes 2, y becomes dy dx? Product rule. I know it doesn't announce itself because it looks like it's just, derivative rules, but we really have to go through a product rule here. Even though it kind of it doesn't seem obvious that there's a product rule going on, but 2x and y, those are different variables. They're being multiplied, and we're asking for the derivative. So we got to go through product rule there. I like to protect that 2xy with a set of parentheses, because once I go through product rule, I get f prime g plus fg prime. That negative is going to end up having to distribute through the multiple terms separated by plus sign there. Okay, but let's go through our derivative rule. We don't do anything special with x's, but when we come across y's, we got to attach that dy dx. All right, so 3x squared becomes 6x. I'm going to get ready for product rule that's going to show up here. Right, f prime g plus fg prime, 2x becomes 2. G stays as y. F is 2x. And then g prime, y's derivative is 1 dy dx. Right, we keep going. 5y squared. We go through power rule for 5y squared, which is 10y. But we're asking for y's derivative, so times dy dx. And don't let constants just stay where they are. They're also impacting remember, every term is getting impacted by derivative. So the 1 doesn't stay a 1. The 1 goes to a 0. Like however many y's you see in the original equation is how many dy dx's should pop up in your derivative equation. Okay, so now it should get a little bit easier. We're done with the calculus. Now we're just trying to find a way to move things around to get that dy dx by itself. So I'm going to distribute that negative through. Okay, so you guys can make progress from here. Leave the two dy dx terms on the left, move the non-dy dx terms to the other side, factor dy dx out, and then see if we can get it by itself. Okay, so I added and subtracted in a way so that my dy dx terms can be together on the same side. Typically, I like them on the left side. Then I factor dy dx out, divide over. You can leave your answer unsimplified on the AP exam, but sometimes their answer choices will probably be simplified. So as long as you know how to get from your version to their version, that's So here I can factor a 2 out and then take the 2 away, and then that should leave me with this term. But free response, this will be acceptable. All right, number 7, find dy dx if y is equal to tangent cube 3x squared. Anyone know what we have to make sure we involve here? Yeah, chain rule. But what should we do so that it makes it easier for us to see chain rule, especially when trig is involved? Put that 3 where? Outside, right? So when you do that, you're not changing the problem, but you are going to make it visually easier to see the outside and the inside a little bit more clearly. If you don't do that, typically it's a little bit harder to see where all the parts are. So if you get that bracket to show up with the cubed outside, then it's more clear. Oh, the outside function is that bracket cube, and then the inside is tangent. I'm going to take turns with each part. Yes. Yeah, that should be a negative 2x. Let me see. 2x. Yeah, I lost that negative there. Thanks. You guess you get that negative x plus 5y. Sorry, I lost it in the division here. All right. Number 7. So let's try this one. We said we can rewrite it. Outside, inside. Okay, we take turn with each derivative. So outside, it's just power rule. Bracket q becomes 3 bracket squared. Treat bracket like its own variable. And we don't change anything with that tangent. Right? We're not ready for that portion yet. Times. Now we're ready for tangent of u. Right? And tangent of u has its own rule. Secant squared u times u prime. As far as cleanup goes, we can put all the non-trig in front. Number 8, find p prime of 1, given that p of x equals f of x cubed. This is also a function within a function. Let's build p prime first, and then we can plug 1 in. So we see the outside is the f, the inside is the x cubed. We take turns with each derivative. F is function notation, but x cubed, we can actually do an actual power rule there. But f just becomes f prime. But when you take the outside derivative, you're not going to make any changes to x cubed because you're not ready for it. Just f prime x cubed times inside's derivative So now replace every x with 1 and see if that will, and see if we can use some of the values they gave us to make substitutions. One cubed is just 1. F prime of 1, they gave us 2. And then 2 times 3 is 6. Number 9, we also haven't seen this in a while, derivative of inverse at a point where you have to use a chart to kind of work your way around. So let me kind of give you a visual representation, remind you of that, and then we can practice this process here. So you don't have to draw this, but just wanted to kind of show you. Let's say I had a function and its inverse. We know that visually, a function and its inverse are ones where they're going to kind of look like they can fold over each other across the y equals x line. So for instance, these will be inverse functions because if I were to fold the graph over each other, over the y equals x line, they're going to overlap. So let's say this is f of x, and let's say this is f inverse of x. One thing that we know between function and its inverse is that their order pair will be flip-flop versions of each other. So if there's an order pair, let's say this is 1, 4, that lives on the function, then on the inverse, there must be an order pair that is what? If there's a 1, 4 here, on the inverse, there must be a what? 4, 1, yeah, so 4, 1. So I like to indicate that in the table to show that, f inverse of A is equal to B, which means that f of B is equal to A. All right, so on the function and its inverse, you're always going to have flip-flop x and y values. Okay, so if we have y for one, it must be the x for the other. If this x for one, it must be y for the other. And then there's also a slope relationship at these points. So f prime of 1 has a slope of 7, which means that the derivative of f inverse at 4 must be what? What's the numeric relationship here? This is a steep slope of 7, but this is a very gradual slope of what? So what's a small positive number that you can use that can involve 7? Over 7. That's the relationship there. So typically what's going to happen is we're going to be working on the function side and gathering that information and then making our conclusion about the inverse. We're not going to be touching the inverse much. We're just using that relationship there. So if I can figure out that f prime of b is equal to some slope, let's say 7, then we know the derivative of f inverse at its corresponding point must be a reciprocal 1 over n. So we typically gather the information, put that in as the y value. We do guess and check to figure out what that x value is. We go through a power rule. We find the derivative. We get that slope. And once you get that slope, we know that the answer we're looking for must be the reciprocal of that. Okay, so number 9. Given that f of x equals 2x cubed minus 3x, h is the inverse of f, then find h prime of -1. So we're going to start here at the bottom right corner here. This is going to be what we're looking for. We're looking for h prime of -1. We know -1 is the x value of my inverse. So I'm going to put my order pair information here. But if -1 is the x value of my inverse, then -1 must be the what of my function? Y value. So I know that f of some unknown x value is equal to -1. So I know that this -1 is not the x value here, it's the y value of the function because of the flip-flop relationship. So we're going to have to go through and solve this before we can move forward, because we do need to figure out what the x value is so we can actually go through and find the information that we're looking for in this space here. So we know that -1 is the y value. So I'm going to just put -1 in for the y and see if I can figure out what the x is. This is not a quadratic, so I can't go through quadratic formula. I kind of have to do a little bit of guess and check. I'm gonna just bring everything over to one side. Now, when you do guess and check, it should be an easy number to find. I would start with 0, see if 0 works. If 0 doesn't work, then try 1, then try -1. And after a couple of tries, you should be able to get your answer here. So 0 doesn't work. 0 minus 3 is -2. -2 plus 1 doesn't equal to 0. What if I plug in 1? If I plug 1 in, I get 2 minus 3, which is -1. -1 plus 1 is 0. That does work. So we know that our x value is 1. So we can go ahead and fill that in. We know if there's an order pair -1, 1 on the H graph, there must be an order pair 1, -1 that lives on the F graph. So if I can find f prime of 1, then this slope will lead me to my answer. So before we find f prime of 1, let's first find f prime of x. Find f prime of x. We go through a power rule. 2x cubed minus 3x, we get 6x squared minus 3. Plug 1 in to get the slope. We get 3. So if this value is 3, then what I'm looking for is what? 1/3. Don't change the sign, just flip to the denominator. Just do the reciprocal. Okay. See if we can try number 10. Number 10, everything is already laid out for you. You just have to kind of map your way around that chart. So let me start you off and see if you can work your way around the chart. So the bottom row is the derivative information, and then the top row is the order pair function information. Okay, if 2 is the x value of my inverse, then 2 must be the what of my function? Y value. So I know that I can put that 2 here, right? So now we're trying to figure out, okay, what's going to fit into this setup that I already have? What can we put here? 1, right? So I know that f of 1 equals 2. You don't have to do this here, but I like to just go ahead and just get that relationship here. If there's the 1, 2 here, there must be a 2, 1 here. So now that I have the x value of my function, if I can find the slope at that point, then that slope will lead me to the slope at the other inverse point. So f prime of 1 is 3. Therefore, the derivative of f inverse at 2 must be what? 1/3. Now, notice that they are giving you some distractors that is not going to be useful. But they're putting that here because they want to see if we understand that this 2 is not the 2 that we're looking for, right? This 2 is the x value of the inverse, but it's not the x value of the function. So this is just a distractor, right? It's not going to help us get to our answer. Next page. Top of the page, page 7, number 1. Function is given. F of x is x cubed plus bx plus 6 times g of x, where b is a constant and g is a differentiable function. And we're given some information here. For what value of b is f prime of 2 is equal to 0? So it's using what we know and kind of seeing if we can put it all together. We're going to treat b like we would a number. So treat b like if it was a 5 or 6 or 8 or 1. Okay. It says, where's f prime of 2 is equal to 0? Let's kind of build it piece by piece, right? We know that we do want to get to our derivative. So let's find f prime of x first. Then we can plug 2 in. Then we can set the derivative equal to 0. And then we should be able to then get that b to work out for us. But if I want to find f prime of x, look at how f of x is set up. What do we have to go through if we want to find the derivative of f of x? Product rule, yeah. We see one set of parentheses, x cubed plus bx plus 6 is being multiplied with g of x. We can't merge these into one term here, so we do need to treat these like 2 separate terms being multiplied. So we got to go through product rule. So I'm going to set up product rule and see if you guys can fill in the derivative. Okay, so f prime, 3x squared plus b, right? Because bx derivative is just b. Imagine this is 5x. 5x will become 5. Therefore, bx will become just b. The 6 goes away. Plus f g prime. F is the original expression. G becomes g prime. So we have our derivative. Let's go ahead and replace every x with 2. We're trying to use f prime of 2. So every x gets replaced with 2. And now we're trying to figure out when is f prime of 2 equal to 0, so I can replace f prime of 2 with 0. Then see if we can algebraically solve for b. Yeah, so this is a good example of a College Board problem, right? Using a concept that you know you're using product rule, but they're just adding a few wrinkles into it to see if you can, it's not your typical product rule. Here's the function, find the derivative. It's using product rule and the derivative process to find a missing piece within this problem. So it's not hard, but it does take a multiple steps that is not your traditional one-step problem, and you find the derivative and you find your answer. Number two, A and B are product rule and chain rule. So you guys can try that later. Number three is just e to the u rule. I want to talk about number four, bottom of the page here. Okay. Again, you guys have your key attached, so you guys will be able to check your answers later on. So if you see a natural log problem, obviously we know the rule for natural log, which is u prime over u. But there's something that that you want to make sure that you want to take advantage of, especially with natural log, and that is expand when possible. The reason why is because that could really save a lot of your derivative steps rather than going through a really messy combination of product and chain and quotient. Sometimes if you're able to expand a log problem, take a really condensed problem, split it up into smaller parts, then the derivative should be easier. So if you see a log condensed problem, right, you want to expand and take advantage of your take advantage of your log properties. So the property that we have, and this is not a derivative process, this is just an expansion process. If I have natural log of A over B, I can expand it into natural log of A minus natural log of B. Likewise, if I have natural log of A times B, I can expand it into natural log of A plus natural log of B. And the reason that we do that is because we're able to take a more complex problem and split them up into easier terms where it should be, just multiple easy derivative rules, u prime over u, to get to our answer. So let's try that here. Take that, split that up into two smaller problems, and then your derivative should be easier to work with. Oh, there's one more expansion property. This is power property. If I have natural log of a to the n, I can bring that exponent down. Sometimes it's helpful to either bring that exponent up or bring the exponent down, but we know we can move it back and forth depending on which will make you progress in your problem. So if I can treat the numerator as my a value and my denominator as my b value, I can do natural log of the top minus natural log of the bottom. And when we do that, we haven't done anything with the derivative, but we have made the problem simpler to work with. Now, natural log of e to the x, we can actually clean that up even further. If you bring that x down, we can do that because we're inside a log expression. And then natural log of e, we know, goes away to a 1. So really, we're just finding the derivative of x minus natural log of e to the x minus 1. So now we can jump into our derivative process. Y prime is equal to x becomes 1. And then u prime over u. A lot easier to do u prime over u here than it was over here when we're stuck inside having to go through multiple chain rules. So u prime over u, my u value is e to the x minus 1, so u prime is just e to the x divided by e to the x minus 1. That's our derivative, but we're trying to match it up with one of our answer choices. We know it can't be A, we know it can't be D. So our remaining options have a combined fraction, so we may have to do that here. Find a common denominator, merge it together, and see if that will make our answer choice show up. So really, this is a 1 over 1. We know our common denominator is just e to the x minus 1. I do need to balance the first fraction, but I don't have to do anything with the second one. So now I have the same common denominator. I can combine like terms with the numerator, e to the x minus 1 minus e to the x. The e to the x's cancel out. So we're left with negative 1 over e to the x. Let's finish with, let's try number 7. Number 7. Trying to see which one could be h prime. So you got a function within a function. The hint is go through chain rule, but there may be multiple layers of chain rule. So see if you can work through that. Okay, so outside first, bracket squared becomes 2 bracket to the first power. Okay. We don't do anything to the inside, right? We're not ready for the inside, not when we're doing the outside portion. Times the inside's derivative. 1 goes away to 0. F of 3x becomes f of u times, sorry, f prime of u times u prime. So f prime of u times u prime. Okay. So if we merge that 2 and 3 together, 2 times 6. Actually, that matches nicely with answer choice D, right? Okay, your homework, pages 5 through 8. Finish up the problems. I'll send out a reminder this afternoon. And again, your key is attached to the back of your packet. Okay, come with your phones.
Yeah. And, but he's also, okay? So frustrated, I went back, I was frustrated, I looked around, it's fine, to go talking, not talking about it. We're right. I found it. Yeah. And then they're having a sale.
I would have thought by it.
So, I'm just gonna order the entire, I'm just float. And I'm sort of. And I believe in the